in the next section, let's see our first actual algorithm for solving the string matching problem. And I call it the brute force method because it's essentially just trying all possible options in a simple problem like this. This might be good enough indeed. But yeah, we'll see that it is not always that great. But it's a good way to start. It's also a good opportunity to think about the problem more generically. Well, what can you do to solve this string matching problem? And so I will assume that what we can do really at this for all the unit except maybe for the last section, last subsection, we can take two characters from the string or from the pattern or from one from the text, one from the pattern, and compare them. Are they the same or not? That's pretty much what we can do. And so we call this a check if we do this between the text and the pattern. I think the notation is not so important. It will always be spelled out if I remember correctly. So we can check two characters, one in the text and one in the pattern. And we can try to confirm or exclude guesses, so positions in the text where the pattern might be found. So you can guess, maybe the pattern starts in the text at position I. So that would be a guess. And there's only so many possible guesses because the pattern can only start at every position. And of course, you can take a guess and then do a few checks, and they might either confirm that there is a match, or they might show a mismatch between some characters, and then you know this is not a correct guess. So a key feature is we need m checks for a correct guess because we have to check all the positions. But we may be much faster with excluding a guess because one mismatch is enough. If we know where to compare to find that mismatch, we can be much quicker. What we'll count in terms of the costs, remember, ultimately it's word RAM, but we want to make our life a little more convenient, so we'll count something more abstract than word RAM instructions. So here I'll usually count the number of character comparisons with the number of checks. We'll later allow some pre-processing, so we'll also compare characters in the pattern with each other, which strictly speaking is not a check according to that definition. But I will still want to count them as character comparisons. So this this equality is fine for the first section, but maybe it should be taken with a grain of salt for later. But an immediate observation from this one is the number of checks can only be at most n times m, because then we have for every guess done all the checks. After at most n times m comparisons, we have compared all possible combinations of text and pattern positions. So if we haven't figured it out till then, we will never figure it out. And so guess what the brute force method does? It tries all the guesses and does all the checks. So you iterate with I through the positions where the pattern could start, and j iterates through the positions of the pattern, and you compare the appropriate characters in the text and the pattern. Now, if you ever find a mismatch, you don't really have to continue that loop. So the brute force method is already not completely dumb. It breaks out of the inner loop if it finds the first mismatch and then returns no match. Well, it skips out of this inner loop and then goes with the next I. And if it has not found a match for any I, it returns no match. And if you ever reach the end of the pattern in the checks, then you have found a match, right? Then you return this position where the match started. Is the algorithm clear? That's as easy as it gets. It's just 2 for loops. Now, interestingly, this is essentially what Java does in the index of method. And there's a reason for that it isn't often as bad. For example, in this, let's maybe play this through quickly. So we would try to find this pattern ABBA in this text. So A matches and B matches and B matches, but then this is a mismatch. So it doesn't occur in the first position. So you try again here, but there's immediately a mismatch. So you don't even have to compare these other three. Same here and here. Then we have to start comparing again. And here's a mismatch. But then we again immediately stop here, whereas here we have to continue longer. And indeed, this is a match. So we have found our match here. And here's the same thing in nicer. So red is a mismatch. If you compare how many comparisons in this concrete instance were needed, it's 15, whereas this worst case n times m is quite a bit more. So it's actually not that bad. Often, if the inputs are not adversarially chosen or you're very unlucky, the brute force method is not unreasonable to take as a start. But for a good library implementation, it maybe isn't robust enough. And the reason is this example. So I said the good thing already about it. It's easy and it's not always bad, but it can be quite bad. In this example, the text is quite boring, and also the pattern is fairly boring, but nobody stops your users from checking patterns, string matching with these inputs. And in this case, you need exactly all the comparisons that you could possibly need. Okay. So nice and easy, not always crappy, but not quite good enough for a robust implementation. We can learn something from this worst case example here. In particular, it seems like at least this worst case has a lot of self-similarity. The text is the same character repeated all over, and the pattern is not too far from that either. So maybe instead of treating this as a bad case, maybe we can take advantage of this fact. And also in some cases here, like you compared A's up to this point, and then okay, there was a mismatch, and it was kind of stupid to start again. But for these next 3 A's, these 2 A's you already checked, and you already know that the text has A's there. So if you were a bit smarter about looking about your pattern first, you would have been able to figure out that you don't have to compare those two. It's clear that they're implied matches. But of course, the brute force method wouldn't be able to figure this out. So what can we do to improve this? There's really 2 big approaches, and the second we'll look at in the next subsection. Both approaches essentially mean don't just start comparing and make uneducated guesses, but instead first spend a little bit of time on analyzing the situation. And that can either be the pattern or the text, depending on the situation. In this unit, we'll treat the situation as dynamic. The text can change all the time, and the pattern is given to us when we query for it, but we assume the pattern is small. So taking some time to analyze the pattern is justified. And so we'll have 4 different ways that take a look at the pattern and try to do something smarter with it than the brute force method. The other option is also interesting, though. If the text can be expected not to change all the time, then you can instead pre-process the text, and that can mean you might be able to find matches much, much faster. And we'll do that in Unit 6. You may have heard of inverted indices or even suffix tree suffix arrays. That's what we'll look at there. This is what's behind search engines, or at least the simpler versions of those. They're the textile websites. Now they do change once in a while, but not so often that you can't recompute this index. But for now, let's stay in the first approach, where the text can change all the time. We have no control. And instead, we're only looking at the pattern before we start matching.